All right, in the next portion of the lecture, let's talk about how we can actually implement convolutional layers in practice. So to just summarize the main ideas about convolutions from the first part, a convolutional layer is basically, it's a way to avoid needing millions of parameters with images, and also to actually learn more efficiently, because a feature that is useful in one position might also likely be useful in another position. With a convolutional layer, we build this little filter and we slide it over every position in the input image. So each layer is local in the sense that each filter only looks at a little region, but it looks at every such region. And that produces a different point in the next activation volume. Each layer produces something you can think of as an image with roughly the same width and height as the preceding one, but a number of channels that is equal to the number of filters. And then you apply your activation function or nonlinearity independently at every position in this three-dimensional volume. Then, if you want to actually reduce the resolution of these layers, which you probably do so that you can eventually produce a single answer, then you want a pooling operation. So if you ever want to get down to a single output, you have to reduce the resolution as you go. The most common type of pooling is max pooling, where you downsample the image of activations at each layer, taking the max in each region. And crucially, the regions here are non-overlapping. So for the convolution, you slide it over every single position, so you have these overlapping filters. For pooling, they're non-overlapping. And this makes it robust to small translational changes too. So if the image moves by a small amount, then probably the max in each region will usually remain the same. Once you've used convolutional nonlinearity pooling to reduce the resolution enough, then at the end, you want to turn it into a fully connected layer. So at the end, you get something small enough that you can flatten it by turning it into a vector, and then feed it into a standard fully connected linear layer, just like we discussed in the previous lecture. All right, so that's the basic kind of idea behind convolutional neural networks. Now let's talk about how we can actually implement all this. We're going to need n-dimensional arrays, which are also called tensors. So all these operations, all these filters, activation maps, images, they will all involve n-dimensional arrays. And the term n-dimensional array is often used synonymously with tensor in deep learning. Now, if you're familiar with tensors from physics or math, you know that tensors have a number of other important properties. They're sort of higher dimensional generalizations of matrices in some sense. In deep learning, when we deal with tensors, we typically use kind of a simplified definition. So you can basically think of tensors as n-dimensional arrays. So for example, the input image would be a three-dimensional array with dimensionality height by width by the number of channels, which is usually 3 for 3 color channels. The filter is four-dimensional, filter height by filter width by output channels by input channels. And the activations are typically also three-dimensional, height by width by number of channels. This is a little bit analogous to the weights and activations that we saw in the standard neural networks in the previous lecture, where we had weight matrices that had 2 dimensions and activation vectors that had 1 dimension, right? So here, the filters, the transformations, always have 1 more dimension than the activations. The activations are 3-dimensional, the filters are 4-dimensional. Typically, the inner or rightmost dimensions are going to work just like vectors and matrices. So if you want a 4-dimensional thing to multiply a 3-dimensional thing, that basically amounts to doing a matrix vector operation for every position along the first 2 dimensions. Matching the outer dimensions, the height and width, basically allows you to treat operations as a broadcast, as an element-wise operation. Convolution, though, is special because for convolution, the height and width don't match. So for convolution, you actually perform a tiny matrix multiply at each position, like a tiny linear layer at each position, and you slide this over every position in the input. Okay? So let's actually work out what that looks like. Let's say that I have an activation A1, and I'm going to turn into Z2. This could also be like A15 to Z16, or it could be like X to Z1, right? Remember the order of activations is X, Z1, A1, Z2, A2, Z3, A3, etc. So this is just one convolution in this chain. So A1 is going to have a dimensionality of H input by W input by C input, or H1, W1, C1 if you like. And Z2 is going to have a dimensionality of H out, W out, C out, or H2, W2, C2 if you like. And for now, we'll just assume that the W's are almost equal, but we'll talk a little bit more about how W in and W out will relate to each other. So there's a few choices to be made there. But for now, let's just say that they're equal and avoid worrying about it. All right. Our filter is specified by a weight matrix W2, only it's not a matrix anymore. Now it's a four-dimensional object. In general, we would also have biases, just like we did with the linear layers, but just like in the previous lecture, I'll omit the biases for now just to keep things simple. But remember, they really are there. There's also these biases. Okay, so what is going to be the dimensionality of W2? Well, it's going to be HF by WF by C out by C in, okay? Because it's going to map C into C out. If we did have a bias W, or if we've had a bias B2, what would be the dimensionality of that bias? Well, it would be HF by WF by C out. Okay, so now most of you are probably kind of getting some idea of what W2 is going to do, but actually writing it out as an equation is not entirely trivial. So W2 is going to be a filter. So if you sort of project into the first two coordinates, HF and WF, you can think of it as a 3x3 grid, but really each cell in this 3x3 grid, if HF and WF are equal to 3, is itself actually a little matrix with dimensionality C out by C in. So it's not just one number, it's actually a little matrix C out by C in. And maybe our activations are this other grid, but again, it's actually three-dimensional, so each point here is a little vector with dimensionality C in or C out. So this is the input, this is the output. The convolution operation is going to take this little filter, place it at every position in the input map, and produce the corresponding position on the output map. So let's write this out as an equation. And I'm going to use this kind of notation, kind of a little bit analogous to like indexing in Python, where I'll put the indices in square brackets just to make it really clear. So we're going to write out the equation for Z2ijk. So this is the position I along the vertical axis, j along the horizontal one, and k in depth. So this is feature k at position ij in the output map. And we're going to obtain it by summing over every position in the filter along the first dimension. So L is going to go from 0 to HF minus 1, so this is 0 indexed. M is going to go from 0 to HW minus 1. And then N is going to go from 0 to C in minus 1. And then we'll have a product between W2 at L, M, K, N. Right? So L indexes the height of the filter, M the width, K is the output dimension, N is the input dimension. So K is going to go from 0 to C out minus 1 and from 0 to C in minus 1. And then we're going to multiply it by a point in the input activation map. And the way we're going to get that point is we'll center it at ij, and then we'll go left or right depending on L and M. So actually writing out the expression for this is a little bit non-trivial. Here is the expression, but let me walk you through it. So how far to the left would you go? Well, if your filter is of width 5, let's say, it's centered at j, we're talking about the horizontal axis, so it's centered at j, and it's of width 5, so that means you're going to go 2 to the left and 2 to the right. So you go 2 to the left, that gives you 2, then you have the center point, that's 3, and then you have 2 to the right, that's 2 more, so that's 5. In general, for each dimension, let's say you're talking about the first dimension, you're going to go HF minus 1 over 2 backward, and HF minus 1 over 2 forward. And then you have the point that you're centered at, so that gives you 1 more. So HF minus 1 over 2 plus HF minus 1 over 2 plus 1 is exactly HF. So the way that you index into the input map is by taking the point I at which you're centered, then adding L, which is where you are in the filter, and then subtracting HF minus 1 over 2. So that means that for L equals 0, you start at I minus HF minus 1 over 2, and then as L goes up, you end up at I plus HF minus 1 over 2. So, and then the last index to A is just N. That's indexing to from 0 to cn minus 1. All right, so this is the expression for how you calculate the value at every point in the output activation map. But remember that that every point in the input and output is a little vector, and every point in the filter is a little matrix. So we could also write this as following. We could say z2 I j, and this is now indexing a vector of dimensionality c out, is equal to a sum over every position in the filter of w2 at lm, and this is now a matrix, a c out by c in matrix, times the vector located in A1 at the same position as before. So now I'm writing out the indices for the locations horizontally and vertically, but I'm using matrix and vector notation for the channels. And this makes it a little clearer that essentially in a convolution you have like a little tiny linear layer at every single position, and you're just sliding this thing across. And then after you do this, of course, don't forget to apply your nonlinearity. So you've turned A1 into Z2 by using a convolution, and now you need to turn Z2 into A2 by applying a nonlinearity to every location independently. And that can be a ReLU or a sigmoid or whatever you want. Typically we'd use ReLUs with convents these days. All right, so this is basically the way that you write out convolutions. Now in practice, these are typically implemented with matrix vector multiplication because it's more efficient in hardware, and there are typically efficient GPU implementations of convolutions because they do tend to be computationally quite expensive. They don't have that many layers, they don't have that many parameters, but they do have a lot of requirements in terms of the number of computations that need to be done, because these matrix vector multiplications need to be done many, many, many times at every location, right? So computation, they're actually quite expensive. And GPUs can speed that up because it's the same operation evaluated at every position, and GPUs are really good at that. All right, so the convolution is simple in principle. You're just sliding this filter over the input image. It's a little complicated to write out, mostly because of the indexing. Right? You have to get the indices just right to express a fairly simple concept with seemingly complex math. Okay, now before we have everything we need to actually use convolutions, there's one last detail, well, a couple of last details that we have to talk about. One of them is padding and edges. So far, I've conveniently avoided talking about anything regarding what happens at edges and corners. Right, so I've told you that you go, if your filter is of width 5, you go 2 steps to the left, 2 steps to the right, and then you grab the middle. But what if you go 2 steps to the left and you go off the end of the image? So what if you end up with negative indices, or indices that are larger than the image width? So this is not a problem in this picture, but imagine that we were centering at one of the corners. Well, what are you going to multiply your W's by for these points that are not actually on the image? There are basically two choices for addressing this issue. One option is to simply cut off the edges, basically disallow the filter from ever being evaluated at a point where some of the indices become negative or larger than the image width. So in this case, if you have a 3x3 filter and a 5x5 image, the result would be 3x3 because those corners would result in these invalid values. That's a perfectly reasonable way to do things, and we can work through a little example to try to understand how this will change the size of the activation map. So if your input is 32 by 32 by 3, and your filter is 5 by 5 by 6, what is going to be the output in this case? Take a moment to think through this. All right, so here's how we can think about it. We could imagine that the filter has a kind of radius, which we can calculate as hf minus 1 over 2. Right? We'll assume that typically our filters have odd number width and height. This is almost always the case. So if you have an odd number width or height, you subtract 1 and divide by 2, and that tells you how many pixels you go to the left and how many pixels you go to the right. So if your filter is of size 5, you can sort of say that 2 is its radius. And if that radius goes off the end of the image, then it's invalid. So the number of locations that are cut off on each side is equal to that radius. So if you have a filter that is 5 by 5, you're going to cut off 2 locations on the left, 2 locations on the right, 2 locations on the top, and 2 locations on the bottom. If your filter is 3 by 3, like it is in this picture, then you're going to cut off one row at the top, one row at the bottom, one column on the left, one column on the right. Okay. So that means that for each dimension, the amount by which the size of that dimension will decrease will be the radius times 2, because you cut off in the beginning and at the end. So in general, the output height, let's say, will be the input height minus the radius, hf minus 1 over 2, times 2, because you pay that price on both ends. So if our filter is of size 5, then our radius is 2, so that means that our 32 by 32 thing will be reduced by 2 times 2, or 4, for each dimension, so the 32 will turn into a 28. So then the output will be 28 by 28 by the number of output filters, which is, in this case, 6, right? Because our filter is 5 by 5 by 6. So we'll end up with a 28 by 28 by 6 output. And if you think back to that picture of Lynette that I showed in the previous part, that's why Lynette actually had these convolutional maps that were going down in size even when you were not pooling. So they start with a 32 by 32 image. They actually do have a 5 by 5 filter, so that gets them a 28 by 28. Then they have 2 by 2 pooling, which gets them a 14 by 14. So when you cut off the edges like this, our activations actually shrink with every layer. And that's generally fine, but some people really don't like this. And they don't like this because, especially once these activation maps get pretty small towards the end of your network, now this reduction can actually be fairly significant. So an alternative that we can use, and this is actually a fairly popular option, is to do zero padding. So with zero padding, you do evaluate the filter on the corners and the edges, and any point that goes off the end of the image or activation map is just replaced with 0. Now this might seem like kind of a strange choice because that 0 will actually affect your result. And it's also pretty important, if you use this, to remember to subtract the image mean first. Right? Because in the input image, typically all of our pixel values are positive numbers. So these zeros that you put in will look a little bit peculiar because they'll be lower than any activation in the original image. So typically what you do to deal with this is you take the average pixel intensity and you subtract it from the pixel intensity at every location so that the image is kind of centered, so that 0 is kind of the average intensity. And that tends to work a bit better. There are fancier contrast normalization techniques that people actually use in practice, but as long as you subtract out the mean, that's probably okay. One advantage of zero padding is that it is in some sense simpler. The size of the activation map is preserved. You don't have to worry about things getting smaller. The disadvantage is that you have this kind of weird zero effect at the boundary. This is usually not a problem, which is why this method is so popular. It's just conceptually maybe a little bit awkward. All right. The last concept I want to go through in this part of the lecture is something called strided convolutions. So the standard convnet structure at each layer that we've discussed so far looks like this. Step 1, apply your convolution to turn your h by w by c in into an h by w by c out, if you're using zero padding. If you're taking off the boundary, then it will be h minus some small number by w minus some small number by c out. Then step 2, apply your activation function. And that preserves the dimensionality because the activation function is applied independently for every single point. Step 3, apply pooling with some width n. And pooling reduces the dimensionality, reduces the resolution by the factor n. So if you have h by w by c out, that turns into h over n by w over n by c out. And w would typically be, 2 or 4 or something like that. Now, the first step here, applying this convolution, can be computationally very expensive. It doesn't require that many parameters, but it's expensive because you're doing this matrix multiply many, many times. In fact, this C out by C in matrix multiply basically happens for every position in the H by W image. So here's an idea to make it a little cheaper. What if you skip over some of the positions? So what if instead of evaluating the filter at every point in the input image, you actually skip a few points? So maybe you start here, then you slide over here, then you slide over here, then you slide over here. So notice here that we're jumping 2 pixels instead of 1 pixel. The filters are still overlapping, we're just jumping further. So this is called strided convolutions. Strided convolutions are a perfectly reasonable choice. The amount that you skip is called a stride. So here when we're skipping 2, this is called a stride of 2. By default, you would have a stride of 1. Strided convolutions are not the same as pooling, because in pooling you do actually compute the activations at every location, then you take the max, whereas in strided convolutions you skip some locations altogether. But unlike pooling, strided convolutions are a lot cheaper computation. And some people think that strided convolutions can be almost as good as regular convolutions plus pooling, but much, much cheaper. In practice, a lot of people still do use pooling, partly because GPUs do make regular convolutions fairly efficient. But if you want really fast neural networks, oftentimes strided convolutions can be quite a bit cheaper, especially early on when the resolution of your activations is very large. So this is an important concept to know about, and we'll see it come up in some of the neural networks that we'll discuss in the next part of the lecture.